So, hey everyone, this is Isaac, and I'm a graduate student and a researcher from Northeastern University. And in this particular video, we'll be talking about the dynamic tanh normalization function, which was introduced in 2025. Uh, it's a really good alternative for the normalization layers that are used in transformer architecture. Yeah, it was introduced by a few researchers along with Yann LeCun as a part of their fair research at Meta. So, to give you a brief context about what normalization is a layer that is very common in transformer architectures. It basically helps in reducing the complexity between the layers in a transformer, and it also helps handling the input information that is passed into a transformer. So there are different normalization techniques available, and they are like batch normalization techniques like batch normalization, min-max normalization, and so on. And I found this interesting blog by I think Sachin Soni, which was a really good blog on what normalization is. It basically tells you how normalization works, how calculations happen, like finding the mean and standard deviation, and then finally getting the output after normalizing the input values. So the reason is mostly because to reduce the amount of computation and make the values within a certain range so that the model doesn't get uh, quite confused or deviated with the input or uh, the input or the outputs in the hidden layers. So then when we move on to uh, when we move on to the paper that discusses transformers without normalization. So this was another video that I found interesting on transformers without normalization, which explains the entire paper. But I just wanted to like review it and then uh, just help you guys understand it easier. So initially, normalization became quite popular in the years to like help transformer architectures understand the information better within each layer. Later, when the researchers understood that uh, the outcome of these normalization layers was in a certain shape that was very familiar to a tan h functions. They determined, okay, maybe a tan h function could replace the function of a normalization layer or yeah, and then they uh, tried to mimic it as much as possible, and they came up with a parameter known as alpha, which helps them come to a conclusion known as a scaled tan h functions, which is very accurate to what normalization layers actually perform. Um, like what normalization layer basically does, and then they give us the equation which normalization layer follows, and later on they try to discuss about different normalization layers like RMSNorm and batch normalization and different normalization techniques which were initially used, and they try to compare it with the dynamic tan h normalization. Um, and then finally they try to discuss about various metrics, the normalization, uh, tanh normalization against different architectures, uh, which will be discussed, I think, in the next uh, slides, as follows. And then they have this code snippet also mentioning different parameters that the dynamic tanh function has. And finally, they they also they finally discuss on different uh, evaluations or different uh, experiments that they ran using the dynamic tanh normalization layer for by passing like 100 forward passes and 100 backward passes using a single sequence of like 4096 tokens. And they observed that the dynamic tan h had lesser inference and training time compared to RMS normalization technique, which is, I think, is root mean square normalization. And then for more information, they more experiments and evaluation, they tried uh, decision techniques like fix up, skip init, and sigma repram, which is other different normalization techniques which are discussed in other research papers across different models like vision transformers, and then MAE self-supervised models. And they also observed in this place that the dynamic tan models, I mean normalization, still perform better than all the other three normalization techniques. So these were some of the insights that they got from this paper. um, yeah, and they set the alpha parameter to zero point 0.5 value as default, and try to compare it with the different uh, different normalization uh, techniques. So in the end, they found out uh, like dynamic tan perform really well compared to other normalization techniques, which uh, which actually improved the performance in very large language models with certain amount of optimization, which is like a really great thing, because they could replace normalization as a whole with just using a tan function and a modified parameter. So when I looked into other applications of this dynamic tan I found out few research papers um, uh, in the internet that actually try to implement this dynamic tan without normalization. So this is the GitHub repository of the uh, the people who found dynamic tan and it was published in CVPR 2025. And it basically tells us like normalization layers are ubiquitous in modern neural networks and have like, long been considered essential. And they found out uh, like transformers often produce tan like S-shaped input-output mappings by incorporating dynamic tan transformers without normalization can match or exceed performance of their normalized counterparts. And this is the code snippet that they gave us with alpha, weight, and bias values and parameters that can be tuned to like match the performance of the normal normalization layer. And so they evaluated it across different architectures, VIT, COV, Next, MAE Dino model, DIT Llama Babe 2x speech model, uh, and so on. So yeah, I'll be dropping all the resources in this video, so you guys can go through it, understand the state of the art research that's going on in artificial intelligence, and some applications that I also found where they try to implement uh, dynamic 10H is in this uh, spatiotemporal transformers for pedestrian trajectory prediction. So this interesting paper from Japan, they try to uh, produce some results for pedestrian trajectory prediction, and they use dynamic 10H for this uh, particular research. And nonetheless, I also found some related to hardware implementation as well, and enhancing intrusion detection for neural network and IoT traffic with dynamic 10H. uh, so these were all some recently published research on dynamic 10H. Yeah, and also this interesting Hugging Face repository that tells us about stable static embedding, uh, the unlocking the potentials of static embeddings, dynamic 10H normalization approach without speedy penalty. So these are all resources that I found related to dynamic 10H, which can be useful for people who are trying to work on transformers and research in transformers. So so this is the original paper, and it has all the GitHub and other repositories. I will drop down all the resources um, in the comments, so you guys can go through it and understand how they came up with dynamic 10H. So I look forward to seeing you all in the next video. um, and thank you so much for listening.